I can see that there is this live that has popped up. Yes.
Yes, I'm just copy pasting the link.
You have to do it in the other link, right? Chat in the other link. That's where people are waiting.
There is another link that is sent in the chat. We are live on that already. I think I'll just start off. Yeah. You're good to go, right, Bunny?
Yeah, people have come here. They have
I've
watched.
shared the link.
Sure. Yeah. We'll start.
Yes, sir.
Yes, yes.
Hello, all. A very good morning to all of you who have joined from India. And good evening to all those of you who would have joined from the US. Welcome to this live session. We are the minutes delay due to some technical glitch. But now we are in action into the live session. Welcome all of you. My name is Vinay Nair, and I'm part of Raising a Mathematician Foundation. Along with me is Dr. S. Muralidharan, who is an eminent person, especially in the field of Math Olympiad. He is a retired computer scientist from TCS and has been involved in Math Olympiad since quite a few decades. So I welcome all of you who have joined online, and we'll start off with this session. Let me start with a quick overview of who we are and what we do. So we are a not-for-profit organization, Raising a Mathematician Foundation, and we have been in existence since last 12 years now. And we work towards identifying and grooming students who are deeply passionate about mathematics and also working towards spreading the beauty of mathematics to people across all ages. And in doing that, there are different initiatives that we run to do that. Some of them are residential training programs, some of them are online courses, some of them are offline sessions like math circles that we have started since last couple of years, and so on and so forth. And this live session is more about International Mathematical Olympiad and how do we gear up for that, and to give a taste of how Math Olympiad looks like and how problems in Math Olympiad looks like, especially for students of grade 8 to 12. So let me start with what is Math Olympiad. From the word Olympiad, we can make a guess that it is something to do with Olympics. So, like in Olympics, how students, not students, participants are selected through various levels of scrutiny and selection, and they represent the country internationally in different sports. Similar is the case with math, science, computer science, and other fields where we have Olympiads, which are the Olympics of those subjects, where students are selected and they represent the country internationally. They compete with over 100 countries when it comes to Math Olympiad, and it's a very rigorous contest. And now, why I'm saying this is because there are a lot of math contests which carry the name Olympiad, but essentially they are all math contests, and we are not talking about those math contests in this session. We are talking about the International Mathematical Olympiad. In India, it is conducted by the Homi Bhabha Center for Science Education, and there are different levels of qualifying tests through which students go through before they make it to the team, right? So let me just give you a quick glimpse about which are the different levels. So the first level is called IOQM. And this is for students who are strictly from grade 8 to grade 12. In India, last year we had about a lakh of students who had registered, about 80,000 students who wrote the IOQM from grade 8 to 12. This year, I believe it was somewhere around 1,10,000. And these students, they went through the first level IOQM, and about 5,000 students got selected to the next level, which is regional mathematics Olympiad, or the RMO, which is one of the most interesting exams I've ever come across, because it has 3 hours and only 6 questions. And these 6 questions are really challenging, especially for those who love mathematics, love the rigor of mathematics. They actually enjoy these kind of problems. So why I'm saying this is because Math Olympiad is mainly for students who are deeply passionate about mathematics, because the problems are going to be challenging. So it's meant for students who have that kind of strong inclination towards math. Coming to the next level after RMO is INMO. And in INMO, students go through more difficult problems, and that is the next level of exam. I think about maybe around 500 to 600 students write the INMO. And from the INMO, about 30 students are further selected for a training camp, which is called IMOTC. And it is a month-long training camp. Since last year, it has been happening in Chennai Mathematical Institute. And from that training camp, 6 students are selected who represent India internationally in the IMO. So you can see this year about 1,10,000 students wrote the IOQM, about 4,000 to 5,000 students were selected for the RMO. From that, a few students, about say maybe roughly around 10% or even less, they write the INMO. From that, about 30 students are selected for IMO training camp, and from that 6 students are going to represent the country, right? So when I say this, many a times those who are new to Olympiad, maybe they'll feel, oh, if only 6 students are going to represent the country, there's a very less chance that I can be part of that. So what's the point in gearing up for this, right? The reason that we want to encourage students to prepare for the Math Olympiad is because if they have the interest and they have the potential, then they should really be challenged with hard problems, and that can only happen if they are exposed to things which are beyond the curriculum. That is what Olympiad offers, right? So we will get a taste of what is the kind of math that students encounter, what is the kind of problems that students encounter in the Math Olympiad, and how do you solve them in the next few minutes. But before I get there, let me just quickly sorry for the disruption. I'll just start over. Right. So I was saying how proud and happy we are about the student achievements that we have. So in 2023 and 2024, we had 20% of the IMO training camp participants who are RAM students. And this year, India had bagged the 4th position in the IMO in the finals worldwide. And one of the gold medalists in that, Kanav Talwar, was part of our Olympiad training program. And we are really proud about these students, and also proud about students who really prepared but who may not have gotten through, but they have been doing exceptionally well even after that. So that is something that I really want to share about. And just yesterday, we got a news that the European Girls Math Olympiad team has been selected, which is a 4-member team. And that again, we have 2 of our girls who have qualified for the team. So congratulations to all of them. So that is something that I wanted to share. And lastly, let me give a quick glimpse before I hand it over to Murli sir. I am sure all of you are awaiting the action in problem solving. So let me just quickly give an overview about the Olympiad training program that we conduct. As you can see in the virtual background behind me, there are different levels. One is Foundation Math Olympiad, which is meant for 6th and 7th graders. And there is Intermediate Math Olympiad Training Program, Intermediate MOTP, conducted by Raising a Mathematician Foundation or RAM Foundation. And there is Advanced Math Olympiad, which is AMOTP. And AMOTP is for students who are aiming for INMO, and Intermediate is for students who are aiming for IOQM and RMO. So if you are a beginner in the Olympiad, then intermediate course is the best course for you. And you should be grade 8 or above. Exceptionally, we have students of grade 7 also in the intermediate program, but generally we recommend it for grade 8 and above. So if you are in grade 7 this year and you are deeply passionate about mathematics, take a look at the past papers of IOQM and see if those are problems that you are interested in, and you can apply for Intermediate Math Olympiad Training Program. Okay, so with that, I'll hand it over to Murli sir, who is going to share with us some problems from 2 of the 4 topics that we have in Math Olympiad. One is number theory, the other is combinatorics, algebra, and geometry. So Murli sir is going to take us through some problems in number theory and combinatorics. And I would invite Murli sir to take this further. Murli sir, over to you.
Thanks, Vinay. And I'm really excited to see so many participants interested in Olympiads. It's really a very nice program. I think my screen is shared. Hopefully, yes. Okay, one second. Just hold on a minute. I'll come back. Yeah. This will be a session which will be introduction to the IMOTP and AMOTP to give a taste of what problems are like basically at the foundation level or even at the IMO level, that is International Mathematical Olympiad level. So we will be taking problems and then walking through them and trying to solve. So how different is an Olympiad training from normal school level curriculum training and so on? Basically, in Olympiad training, we aim to teach you something called PSTs. So what's a PST? It's basically a problem solving technique. Okay. So this is a problem solving technique. So we will be seeing a lot of techniques. And then each technique is based on certain theorems or certain results of mathematics. But actually what will happen is that in the course of this training, you will yourself come up with some problem solving techniques of your own, and you will be applying them while solving problems. And to give you a taste of what problem solving is all about, and let's hear a really very eminent mathematician, Mariam Mirzakhani. And in fact, she is an Iranian mathematician who passed away at the age of 40. And she is also a Fields Medal winner. Fields Medal, of course, you know that is the highest prize a mathematician can get in mathematics. It's considered equivalent to the Nobel Prize. There is no Nobel Prize in mathematics. It's like, what is problem solving? It's just like being lost in the jungle and trying to use all the knowledge that you have, that you can gather, to come up with some new tricks, and with some luck, you might find a way out. And she was talking about research level problems, but for the INMO level or IMO level problems also, a similar experience with a shorter scale will apply, because in INMO you are given 3 problems to solve in 4.5 hours. So when each problem is supposed to take 1.5 hours or more, then you know that the difficulty level as well as how tricky it may be to find a correct strategy for solving the problem. So problem solving techniques is basically the key to solving problems of this type at this level of the competition. Okay, so let's look at a simple one first. Let's find the number of ways of choosing 4 books, no two adjacent, from 13 books arranged in a row. We'll assume that all the 13 books are different, and then all the choices, meaning when I choose a different book, the choice is different and so on. So I have 13 books in a row. Let me say the books are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So I have to choose 4 of them. So I have to choose 4, and no two must be adjacent. For example, if I choose 1, I have to choose 3. And once I choose 3, I can choose 5 or something like that. Okay. But one way to get this done may be to list down all of them. For instance, it could be like 1, 3, 5, 7, 1, 3, 5, 8, 1, 3, 5, 9, etc. So we can try that, but we don't know how many will be there. And then of course the maximum will be quite a lot of thing, because I have to choose 4 out of 13. So at least the maximum number of choices is 13C4, which is a huge number. That is 13 into 12 into 11 into 10 by 1 into 2 into 3 into 4. So even if I simplify this, this is 55 into 13. This is 65. And I think 715, isn't it? Whatever. So I can't list down all of them, and then that's not a good idea at all. So that's not a good option, good strategy for solving this problem. The other strategy may be that I can try what happens if I count how many ways. See, again, 4 is become a bit of a problem, because 4 books not adjacent is not very good. So how many ways I can choose? I can choose 2 books that are not adjacent. So 2 books are not adjacent means I can do like this. It could be 1 and 3. So it can be listed down also. Let's look at how we can list it down. And I can list it down like 1 and 3, 1 and 4, 1 and 5 up to 1 and 13. Or 2 and 4, 2 and 5, etc. up to 2 and 13. Like that I can list it down also. So if I list down, I can be easily to count, but this looks also is a good strategy. But the thing is, again, I have to do a lot of work. So let us put on the thinking cap and then do something else. Now I want 2 books that are not adjacent. So can I count? That is actually something called the count the complement. Count the complement means, can I count the choices which are not adjacent? That means I have 2 books here. I have to choose that the things are not adjacent. So if I just total I already know that is 13C2 is equal to 13 into 12 by 1 into 2. So this is 6. This is so this is 78. Okay, I am notoriously bad in meaning multiplication and division. So don't get me. If I'm doing something wrong, then please correct me. So this total is 78. And if I just look at the complement thing and then subtract from this total, I will get the answer, correct? So what's the complement? Complement means I have to choose two books that both are adjacent. So that is very easy to list. It's 1, 2, 2, 3, 3, 4, 4, 5, etc. up to 12, 13. There are 12 choices for the complement. That is, I have 12. I can choose two books out of 13 books in such that both are adjacent to each other. There are 12 choices. So this is 78 minus 12, which is 66. So for two books, it is the same. It is 66. Now the 66 is sort of a, it just is something, is a 66. Actually, I had to see what the 66 is. So let me say this 66 is something like, can I say it is same as 12 into 11 by 1 into 2? So 12 into 11 by 1 into 2. This is same as 12 choose 2. So this 12 choose 2 seems to be a sort of a very short and sweet answer. It's a compact answer as that. So what it means is that the number of ways of choosing two non-adjacent books is same as number of ways of choosing 2 out of sum 12. So what is this sum 12? Which is this sum 12? So if I find that sum 12, out of which I can choose 2 of them, then positively that would be same as choosing non-adjacent books. Okay, that's what it looks like. So what is this 12? I have to find out. So I have these books arranged in a row: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I am going to choose two books. So whenever I choose a book, I'll put a C below that. And whenever I don't choose the book, I will put a R below that one. So I will have two C's somewhere here, and then the rest will be R's. The rest will be R's. I have this R and this R, this R, this R, this R. So how many R's I will have? So I have 13 books totally, and I have two C's. I have two C's, and the rest are R's. So I have 11 R's and two C's. What's the characteristic of these two C's? The C's cannot be together. That means if I have a two C adjacent to each other, that means I am choosing adjacent books. So the C's have to be between two C's, there will be at least one R. So I have to arrange in such a way that I have to arrange 11 R's and two C's in such a way that the C's are not together. So what I will do, I will just arrange 11 R's first. 5, 6, 7, 8, 9, 10, and 11. And out of these 11 R's, I have to put two C's somewhere. Where all I can put a C? I can put a C in between these gaps. In between the gaps between the R's. Because once I put one C in those gaps, two C's in those gaps, then I would have mapped that to a choice of two books not adjacent to each other. So when I do that, what happens? So I have 11 R's here. There are 10 gaps in between the R's. There is one in the front and there is one at the back. So I have 12 choices. That is 12 choices. What are the choices? The choices are the gaps. The choices are the gaps, out of which I have to choose two of them. And how many ways I can choose 12, 2 out of 12? Of course, 12C2, which is basically 66. And does it work for 4 books as well? Why not? I have 11. In that case, how many? I have chosen 4 books there. That means how many R's will be there? There will be 4 C's and then 9 R's. So I am putting 9 R's here. I am putting 9 R's here. Now how many gaps I will have? I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 gaps in between, one before and one after. So I have totally 10 gaps, out of which I have to choose 4 to place the C's they have 10C4. So this means, so I have already solved this problem of 13 books. So if it is 13 books, and the answer will be 10C4. So note that we looked at a simpler case. In fact, most of you would have heard about the Hungarian mathematician by name George Polya. He wrote a book called How to Solve It. It's about 100 years old now, but still it is relevant for most of us. And there he just enunciates 4 problem-solving principles. The first problem is that, of course, the first one is that read the problem. Read the problem. Okay. And the second one is that if you can't solve, find a simpler problem. Find a simpler problem you can't solve. And as you solve that problem, you will definitely get an idea towards the original problem. So that's what happened here. So we wanted 4 books, and then it looked like a bit of a tough choice. Meaning, of course, if I had 4 books, means I could have chosen 1, 2, 5, and then let us say 10 also. So this also I would have chosen. So that choice is a bit difficult to get by. So we found a simpler problem, which is 13 instead of 4 books. I wanted to choose 2 books, which are not adjacent. And there we arrange, meaning there we could enumerate it pretty easily here. And that enumeration, and of course, we had a hard look at this number 66 and then observed that this is something like this, and which you already know as n minus 1, meaning 12C2. And from there, we sort of guessed what could be the answer. Okay. And then we just eliminated, we just found out that how to get that answer in a quick way. So again, note that this 13 and 4 are no sacred numbers. So if I have, let us say, n books arranged in a row, and I want to say k books to be chosen, then what I have to do, it will be n books and k books. So there will be n minus k R's and then k C's. So arrange n minus 1 k R's here. And then the number of gaps will be n minus k minus 1 in between, 1 before and 1 after. The total number of gaps is n minus k minus 1 plus 2. And I want to choose 2 out of that. So I have to choose k out of that. So n minus 1. So the answer is n minus k plus 1 ck. So just by looking at the 2 case, and we could not only solve the problem given, but also we solved it in a cleaner way. And of course, we could generalize to n and k. So most of the time, that's what happens. That is, if you find the right simpler problem, then probably you not only solve the problem, you find a better solution and then the better generalization as well. Okay, right. So let's look at, I hope you enjoyed this problem, and I can't resist myself to ask you this question. Suppose you want to choose 4 books out of 20 books, arranged in a row, so that any 2 chosen books are at least 2 books apart. At least 2 books apart. Now you can think whether the same technique of putting, I have 20 books and 4 books, so I will have 16 hours. I will have 16 hours, and then I have to have 4, this is 16 hours, and then I will have 4 C's. And then in this case, now it's not only the gaps. So if I put a C here, suppose I have my RC, then the next 2 things cannot be this. The next gap cannot be put. Next gap cannot be put, and so on. So can I use the same technique for doing this also? Perhaps not, because this looks like a slightly, even though I have just made only one change, 2 books apart, instead of they are not adjacent, which is 1 book apart. So if I take 2 books apart, then probably I think this looks like a different problem. I at least a priori it seems that there are the previous technique may not work. Correct? The previous technique may not work, or will it work? Right. Let's see whether it can work or not. So I have, let us say I have, let me name them. I have G1, G2, and G, how many gaps will be there? I have G, uh, 16 gaps, so that 14, no, 16 gaps means what? It will be 15 gaps in between 17. So I have G16 and G17. I have, is it right? I have, let us say I have 16 hours. So if I have 2 or 1, so this is 16 hours. That means I have 15 gaps, and okay, I have these many gaps. Out of which, whenever I choose one gap, I can't choose the next gap. I can't choose the next gap. So I'm just looking at only the gaps arranged like this one. Gaps arranged like this one. Now I have to choose 4 out of this. I have to choose 4 out of this, and here is the critical one. That is, no 2 gaps, no 2 choices can be adjacent. Correct? If I choose only these 2 adjacent gaps, there will be only 1 book in between. So if I don't choose this one, suppose I have choose this G1 and G3, definitely there are 2 books in between. So at least, of course, if I choose G4, there will be 3 books in between. So what I need is that this reduces to the previous problem. Now, instead of previously I had 13 and 4, now I have 17 and 4. I have 17 and 4. So now we had the formula for n minus k plus 1 ck. Here what I have here, I have instead of 17, instead of n is 17 here. So this is 17 minus 4 plus 1 C4. So this is 18, so it is 14 C4. This is the number of ways of choosing 4 books such that no 2 are adjacent. Now, this looks like a different problem, but it just reduced the previous problem by looking at the gaps carefully. Of course, you can also generalize this to n and k, and then you can find out the formula yourself, meaning because the ideas are very clear in this case. Now, if I extend it once more, like this, what if the books are arranged in a circle? Okay. So in that case, can we reduce it? Perhaps, and that's for you to think. So you can just play around with this problem and think for this, and then see whether you can get an answer. Of course, don't do for 20 books and 4 books. Do it for n books and then k books, meaning n total books and then k choices. So if I do that, then probably I think you will understand more about these kind of problems. Okay, right. Now let's go to a different, a simpler problem in number theory.
Excuse me, Murali sir.
Yeah.
If I may just interrupt. Yeah. So just a small comment on the earlier problem. So when we read the problems, if we are doing Olympiad for the first time, right, the first thing that it may hit is, oh, there are so many possibilities. How do I even compute all these technique? I mean, all the possibilities, right? And what you are sharing with us is quite insightful because it shows that one is it shows a strategy, as you rightly said. You start with a problem that is still difficult, but maybe that is achievable, which is a slightly lower level difficulty problem. And then you move ahead and start trying that particular problem, right? So this is one great strategy that one can employ.
Hmm.
And the second thing that I think I could see is the I mean, when we look at the math is not that hard to do, right? The
Hmm.
math is not
Hmm.
that hard to do, but
Hmm.
to get that idea, to get that starting point on how do we go about it, that I felt is the hardest part for a beginner. So just wanted to share, get your thoughts
Yeah.
on this before we
Yeah.
move ahead. And
That's
meanwhile, I'll
the.
also encourage our YouTube viewers to put
Hmm.
their questions or comments in the YouTube chat. Yes, Murali sir, over to you.
Yeah. No, actually, this is the key thing here was that writing the 66 as 12 into 11 by 182. So that trick actually you sometimes no you as you do combinatorics and then you some of those numbers become very friendly to you. So by looking at 10, you'll always say that it's 5C2 or 5C3 and so on. So these things become very sort of second nature for a very serious student. And and I'm not saying that it's a trick. It's basically an observation. It's an insight. So those insights, as you go along, as you solve more and more problems, will automatically come to you. In fact, this problem has 9 different ways of solving. We looked at only
Wow.
one of them. Okay, there are 9 different
Wow.
solving, and then each of them have their own generalizations. For instance, the one which the gaps, placing the C's in the gaps, that gave us one level of generalization to the next problem, which is uh, at least meaning no two books are, meaning each of the choices are at least 2 books apart and so on, or at least 3 books apart, and all those things we can do. But this method, will it work for solving the circle problem? Maybe not. We do not know. Or, in fact, there is one more general problem. I don't know. You can just search the name. It's called the Menage problem, which has a similar character, which is arranging n couples in a circular table such that nobody is sitting next to his or her spouse. This is a very hard problem, but the technique used is slightly different than what we used here. But it can be looked at as a generalization of this problem as well. What I'm saying is that there are one in combinatorics. The beauty is that if you change a bit, it becomes a very hard problem, and then if you change the strategy a bit, we can get a very hard generalization as well. So those are the key spots in this one. In fact, I shouldn't brush aside that all these things will come to you with experience, not necessarily. And then these things will definitely come as you solve more and more problems, not by seeing more and more problems. So let me uh, so it is not seeing more and more problems getting solved, but as you solve more and more problems, then only you will get this kind of thing. And again, when in problem solving, actually, if you have tried it for a hard long time, and then your subconscious mind takes over, and then you get the solution in the most unexpected moment. Like for instance, when you are taking a bath, or when you are going to the school, or sometimes, meaning when you are even seeing a movie. So those things, those are these what usually Polya calls the aha moment, and they are extremely satisfying. And then till that aha moment, you are frustrated that you can't solve the problem. But the moment that frustration lifts from you, that's the moment which you cherish, and then you will always remember that solution. Okay, so that's the beauty of this problem solving. Okay, let's go to the next problem, which is in number theory. Yeah, one more comment Vinay sir made, that is that maths is not very tough, but the strategy is very hard to get. Wait till you see the fourth problem, the next problem, where there's almost no math at all. Okay, so that I will tell you what it is.
Wow. I'm curious. I'm
But
curious. Yes.
pure ingenuity, nothing else. Okay,
Wow. Okay.
that we will see the next. So this is okay. Let's look at this problem. Find the smallest positive integer such that the product of its digits is 10 factorial. So for those who don't know what is 10 factorial, it is basically the product of all the numbers up to 10. 7, 8, 9, and 10. So this is the product of all
So,
the.
sorry, sir.
Mhm.
So, this exclamation mark, you gave a name for that.
Yeah, it's called factorial.
Okay.
It's 10 factorial. There are
You also wrote 1 dot, 2 dot, 3 dot,
that is multiplication. That is, if you want
multiplication.
2 into 3,
Okay.
4 into 5 into 6 into 7 into 8 into 9 into 10. Okay. In fact, if you look at the older books, the 10 factorial is usually written in this form. Yeah, L and then a 10 and so on. But normally these days, most of the textbooks use this kind of symbol. Okay. Right. So I want the smallest positive integer. Of course, one integer is basically 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9. I can't have 10 as a digit, so I need to include it as 2 into 5. This obviously is a number, that is the number is 2, 3, 4, 5, 6, 7, 8, 9, 2, 5. Definitely this is a smaller number. This is a number, but this is not, I don't know whether it is small. And again, there's a smaller number than this, which is 2, 2, 3, 4, 5, 5, 6, 7, 8, 9. This is a smaller number. Correct? This is a smaller number. And there's still a smaller number, which is 3, 4, 4, 5, 5, 6, 7, 8, 9. This is again a smaller number. Correct? Or there can be a smaller number also like this one. 2, 4, 5, 5, 6, 6, 7, 8, 9. So this has 1, 2, 3, 4, 5, 9 digits. This also has 9 digits, but this is smaller than this. So how long we have to go like this? Right? So we are looking at for the smallest number. Now, this product, let me write down the factors, prime factors of this one. There are 1, 2, this is 2 twos. Okay, let me write down 2 twos, 3, 4, this is 3 twos. So I have 3 plus 1, 4, plus 2, 6. How many are there? There is one more. So 8. So I have 2 power 8. And I have a 3 square here, another 3 here, another 3 here. So I have 3 power 4. And then I have a 5 and a 7. And what else is there? 3, 5, 7. That's it. So 2 power 8 and 3 power 4 and 5 and 7. So there must be one more 5. There's one 5 here, one more 5. So 5 squared is 7. 7 occurs only once, 5 occurs twice, and 3 occurs 1, 2, 4 times, and then 2 occurs 8. So this is the prime factorization. Now we can't argue with these two because I can't simplify them as digits, which gives me this product. So I need 557 in this one, obviously. 557 in this one, obviously. So I have to fill up the other slings as small as possible. So I'm left with only 2 power 8 and 3 power 4. So how can I must be able to combine, most 2s and 3s so that I get a digit. So one way is that I can combine this one as, that is 3 square into 3 square, which is 9 into 9, 2 nines. And this one I can write it as 2 cubed into 2 cubed into 2 square. That will be 4, 8, 8. So if I do that, what will I get? 4, 5, 5, 7, 8, 8, 9, 9. So how many digits are there? 2 plus 2, 4, 8 digits are there. But is this the smallest number? Can you do something better than this? So what I have combined is that, see, if I look at this 2 power 8, or we can do one thing also. That means I can say 2 cubed into 2 cubed. And instead of I have 2 square is left behind, I have a 3 power 4. I can split this 3 square and then I can list the 6 and 6. Instead of this, what I can do is that I can do this as, instead of this number, what I can do, I have a 8 and 8. I have a 8 and 8. And I have only one 9 now. Only this is a 9. And I have two 5s are already there. And I will have two 6s. Two 6s. And anything else is remaining? Two 6s. Two 8s are there. Of course, I need a 7. And so I have 5, 5, 6, 6, 7, 8, 8, 9. So this looks like, what is this number? This is 3 plus 3 plus 2, 8. This also is 3 plus 3 plus 2, 8. But this number is smaller than this number. So this splitting of combining 3 square first and then 2 into 3 and 2 into 3 doesn't seem to work. Doesn't seem to give me a large, smaller number. So this must be the smaller number. That is 4, 5, 5, 7, 8, 8, 9, 9. So this is the smallest number which we can say is the product is factorial 10. So here, if you look at the strategy, initially, of course, writing down one number is pretty easy. Of course, that one may not be the smallest one. Then the key was that here I factorized that one. And again, which factors we can't argue at all means these things that can't be argued at all. So only thing is I have to find what is the smallest number that will get this as the product of digits, 2 power 8 into 3 power 4. In fact, there is a more difficult problem which involves this kind of strategy. But anyway, I will not go there because we're too long way off from here. Okay. Right. So in this problem, what we did was we more or less searched for the number, and we had a strategy of splitting these factors into digits, so that the product becomes the same, this one. So that's what we did. And then we have, we got that as the smallest number. Hope I am right. Let me check. Yes, so it is 4, 5, 5, 7, 8, 9, 9 is the smallest number. Okay. All right. And hope you like this one. So let me go to the next one.
If I can just quickly jump in. Yeah. So if you can just scroll up, I mean, this is just some comments from the YouTube chat. So if you can just scroll right, yeah. So we have 2, 4, 4, 5, 5, 6, 6, 7, 8, 9, right? So this answer was given by Mr. Biraj Vishnu in the chat. And the one that is there in your PDF, a little down in the next slide, that is 4, 5, 5, 4, 5, 5, 7, 8, 7, 9. Right. I think that's a little below.
Smallest,
right. Yeah. This one. Right. But instead of 4, 5, 5, 7, 8, 8, 9, the answer was 4, 5, 5, 7, 8, 7, 9. So I just had a quick question. So 4, 5, 5, 7, 8, 7, 9.
No, 7, 8, 7, 9 can't be there because there are no two 7s in the product, right?
Ah,
This product
right.
is not factorial 10.
Right.
So this is actually
Right.
400 into 49 into 8 into 9. So this is not the factorial 10.
Right.
Yeah, that's not there.
Got it.
Okay, so this is not.
Okay.
Yeah.
I think we have a quite a good engaging lot in the audience.
Okay.
So yeah. Yes,
So,
sir. Please continue.
So
Yeah.
the next one is International Olympiad problem from 1993. It was the third problem on first day. So you know that the International Olympiad occurs on 2 days. The first day you have 3 problems, second day you have 3 problems. Usually the third problem in any day is supposed to be the hardest. It so happened that this is the hardest. I will tell you why it became the hardest also, because it doesn't involve any hard math at all. It just involves a simple strategy and let us say its ingenuity of the highest order. Of highest order. Of course, there is one thing you have to know. I will also tell you what that is. So this is basically ingenuity of the highest order. So some of the problems which appear these days in IMO as well as INMO have this kind of thing. That is, there is no background required to understand the problem at all. And again, there is not much of theory needed to solve the problem. Here it needs only one theory, one fact. And the rest is just sort of playing a game. That's all. How well you play a game is what it is about. Hey, look at this one. So let's read the problem. An infinite chessboard. A solitaire game is played as follows. At the start, we have n square pieces occupying a square of side n. So what we have, suppose if I take 5 by 5, so the chessboard is infinite, but in some portion of that, I have, so this kind of, I have pieces on all, I have n square pieces placed like this. Okay, and a game is played like this one. That is, each time, that is, the only allowed move is to jump over an occupied square to an unoccupied one, and the piece which has been jumped over is removed. So this is the usual rule in many games. For instance, here, this is an unoccupied square. This is an unoccupied square. So I can jump over this square to this square and then remove this square. Or I can jump over, so this to this square and then remove this square. So this is what we have to do. And the question is, for which n can the game end with only one piece remaining on the board? Okay. So let's look at some simpler cases. N is the meaning. I want to find all the values of n. But let's say whether we can play the game for small values of n. Suppose I have only one piece. I have only one piece. Obviously, there is nothing to play. This is trivial. Trivially, the game ends. If I have two, n is 2, see what happens? I have one here, one here, one here, one here. Now, I can jump this piece over this one. So what will happen? So this one will be deleted, this one will be deleted, and only one will be remaining. So here there's a piece. Again, I can do the same thing. So I can delete this, and then put a piece here. Now I have, this is a vacant piece. So I can just jump over this one and then delete this intermediate piece. So I have this. So in this case also, for the n is equal to 2 case, it ends with one piece. Let's look at for n is equal to 3. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So they have 3 square pieces remaining on the board. Assume that, of course, be aware that this is an infinite board. There are plenty of vacant spaces and so on. So I can start removing this one. So I can just delete these two and put a piece here. Okay, put a piece here. And similarly, I can delete these two and put a piece here. And I can delete these two and put a piece here. I can delete these two and put a piece here. And I can delete these two and put a piece here. I'm sorry. Put a piece here. Okay. And I can delete these two and put a piece here. I can delete this one, and put a piece here. And again, I can do the same thing. I can delete this and put a piece here. And now I can delete this and put a piece here. Now there is no play at all. There's no play. There are only two pieces remaining, and I can't jump over anything because there is no adjacent piece to jump over. Okay. Probably I think we made a mistake. We made some wrong choices for doing that. And probably I think we should revisit how we can play in a different way. We can try. Probably I think we can start with this one first, and then this one, and I can put a piece here, and let's say what else? Sorry. So I can delete this and put a piece here. I can delete this this and put a piece here. And I can delete this and put a piece here. And again, I can keep on doing that, and this one, and then put piece here. And then I can again delete this one, put a piece here. And again do this one. Delete this, and put a piece here. Then also I get the same. I am left with two pieces. Can we do this at all? Meaning, if n is equal to 3, it looks like the game doesn't end with one piece. Okay. So if at all, meaning, of course, n is equal to 3 is one. We are not yet sure because we have not proved anything. We just played around for a for a while and then said that n is equal to 3 doesn't seem to work. Okay, what happens n is equal to 4? We'll come back to n is equal to 4 later on. Let's look at this ones by removing. Suppose I have 3 pieces like this and 1 piece like this, and it's like an L. And if this space is empty, I can remove all these guys, because what I will first do is that I will just delete this. I will jump over this one. Sorry. Okay. I will jump over this one. So to get a piece here, and I have to delete these two. Then jump over this one to get a piece here, and then delete these two. And again jump over this one and to get a piece here, and then delete these two. So if I have a situation like this, I can eliminate these 3 cases. And note that this piece will remain at the same. After elimination, it's just like just looks like a sort of a killer. So it just kills one at a time. So this kills first this one, and then this one, and this one, and so on. So it kills those 3 things, and then comes and sits back at the same spot. That's very important for us. So so that means whenever I have an L with this spot vacant, and these 3 will be killed by this one, and then it will come back and sit at the same place. So let's look at this 4 by 4. So I have an L here, and this spot is vacant. So this will be killed, and then this will remain. Correct? This is what this becomes that. Again, I have an L here, and then, so these 3 will be killed, and then this will sit at the same place. And again, I have an L here, and this spot is free. So these 3 will be killed, and I will get here. And again, I have an L here. Note that this spot is free. So this will be killed. Okay, so I will get this into there. And then I have an L here. And then these 3, again, this spot is free. Therefore, this. So I have left with only one of them. So for 4, so for 1 can do, 2 we can do, 3 we do not know, 4 we can do. Okay. So can I do it for 5? Let's look at for 5. So I have 5 here like this. Okay. Now, let's look at this L. This spot is free. Therefore, I can kill these things. These things can be killed. After killing, this guy goes and sits in the same place. And again, I have an L here. This spot is free. And so these 3 things will be killed. So this will be killed. So this will be, these things will be killed. Of course, the same place. So now I have a 4 by 4 here. As I have already seen, 4 by 4 can be reduced to the bottommost corner. That means it can reduce to this one thing. So it will be reduced to this one. It will be reduced to this one. Sorry, reduced to this one. So what is left now? We are left with a 2 by 2 because all of them would have been gone by that time. So by 2 by 2, we already know it game ends with one thing. So what I have here is that for n is equal to 5, I can do that. For n is equal to 5, I can do that. So 6, we do not know, and so on. Okay? We do not know about that one. Okay? Now, this gives a strategy. So 1 and 2 is possible. And then if I have a, somehow, if I can reduce an n plus 3 by n plus 3 to n by n, then I could have proved that anything, whenever n is either 1 mod 2 or 1 mod 3 or 2 mod 3, I will be okay. Because when I start with, let us say, 10 by 10, this will be reduced to 7 by 7. This will be reduced to 4 by 4. Anyway, it's okay now. Similarly, if I have, let us say, 23 by 23, this will reduce to 20 by 20, then 17 by 17, and then 14 by 14, and then 11 by 11, and then 8 by 8, and then this will be 5 by 5, it will be 2 by 2. So again, it's okay. If I start with, let us say, 22 by 22, this will be reduced to 19 by 19, and then 16 by 16, then 13 by 13, then 10 by 10, 7 by 7, 4 by 4, and 1 by 1. That's okay. So if I can somehow show that there's a strategy to get this guy to this guy, then I would have proved that for all n equal to 1 or 2 mod 3, the game ends. The game ends with one piece. That's what I would have proved. We'll look at this n equal to 3 over 3 at a later stage of time. That is very easy because I can just reduce an n plus 3 by n plus 3 board. In this way, I can arrange. So note that our L rule. Whenever I have an L and this space vacant, I can just kill all these three and then this one, right? So I have this n by n here. I have a 4 by 4 here, and I have 3 here and 3 here. Okay, if this is my n plus 3 by n plus 3. So using this L, I can kill the last row. I can kill the last row. Again, using this cell, I can kill this row. I would have killed all these rows. Similarly, I could have killed all these rows. Now I am left with this 4. And this 4, I know that this could be reduced to this one single cell. I can kill all these guys also. So by n plus 3 by n plus 3 can be reduced to n by n. So I have already established that for all n equal to 1 or 2 mod 3, the game ends. So what is left is only when n is 0 mod 3. This is the only place in all these things before, there is nothing, not much of maths, only of sort of a solitaire playing. That's all. Nothing else is there. And of course, a bit of ingenuity in arranging like this and so arranging this way. So just we played some solitaire on the chessboard, and then we could get to reduce that. When n is 1 or 2 mod 3, we can end the game with only one piece. But for 0 mod 3, let's see what happens. We already saw that we have bad experience with 3 by 3. Suppose n is 0 mod 3. We are going to show that it is impossible to leave a single piece in the board. So this type of something can't be done are always tricky, in the sense that we need some strategy to say that something cannot be done. See, something can be done, it's a straightforward proof. But if something can't be done means whatever be your game playing, you can't reduce it to one piece. That's what I have to show. That's a bit more trickier to show. We are going to learn that one. There is a concept of invariance. So what this means is that, particularly in gameplays, whatever way you play the game, something remains the same. Remains the same. If I can find that something remains the same, and that thing, that value of that something is not compatible with the 3 by 3, then we are done. So for that, we are going to introduce four quantities. It's very simple to do. X is 0, 1, 1, 0, 1, 1, and 0, 0. So there are 4 quantities, which is 0, 1, 1, 0, 1, 1, and 0, 0. This may X, this may Y, this may Z, this may E, let's say. So I can add 2 things by, if I add this and X plus Y, I get 1, 1, which is Z. If I add Y plus Z, I will use modulo 2. If I use modulo 2, I will get 0, 1, which is equal to X. If I add Z plus X, this is my Z and X, I will get 1, 0, which is same as Y. And of course, my X plus X is equal to E, Y plus Y is equal to E, and Z plus Z is equal to E. Okay? Z plus Z is equal to E. So we are going to place these symbols X, Y, Z in this n by n board wherever we have a piece. We have a piece. That means I have this, I have my 6 by 6 board here. To start with, all the cells have this piece on them. I'm going to place X, Y, Z in this order. Now, if I add all of them, suppose my S is the sum of these symbols, sum of the symbols on cells having a piece. Let's calculate what this sum will be. How many X's are there? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 X's are there. And 1Y, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 Y's are there. And obviously 12 Z will be there because the total is 36. So if I add all of them, that is my 12X plus 12Y plus 12Z is equal to, so note that any 2 X plus X itself is E, so 12X is E. This will be E plus E plus E, which is E. Now, whenever I started playing the game, let's see what will happen. Suppose if I am going to, suppose this space is vacant. Suppose this space is vacant. There are 2 things in these 2 things. So originally it will be contributing X plus Y, which is equal to Z. After that, this will be again X. Okay. So if I just move this over this one and then eliminate this, what will happen? So this case, this was Z, and previously it was X plus Y. Now these 2 things have no piece on them, so I will not be adding X and Y to Z, S now, but only adding Z to that one. So the top, let me repeat again. So if I am playing the game, when I play the game, how will I play the game? If I have pieces here and here, and if this one is vacant, so I just move this piece and then delete this piece. So what will happen is that previously the X plus Y will be in the sum because they have pieces on the cells. Z will not be in the sum. So now X and Y both will go away and then Z will come to the sum. That means the sum will be remaining invariant. So S will be whatever the way in which I play the game, as long as I abide by the rules, this S, which is the total sum of all the symbols in the cells which have a piece, will be invariant. Now, we are almost done. So what's the original sum? When all the things are there, it is E. Suppose the game ends with only one piece. It will be either X, it will be at Y, or it will be Z. So what will happen to the sum S? S will be either X, Y, or Z. But S cannot change at all because this one is invariant. It remains E all the time. It remains E all the time. That means I cannot reduce it to what? Only one piece. I can reduce it to two pieces. For instance, it could be either here and then here. That means it is X plus X, which will be. It could be again, it will be Y and then Y, like that. That also is possible. So Y plus Y. So it will be at the same, it will be, if at all the game ends, it can end at either two pieces where the symbols on those two pieces will be the same, or it can also end with three pieces like this, X, Y, Z, where the sum is X plus Y plus Z is obviously. So either way, so the game cannot end with one piece. It can end with two pieces or three pieces also. Okay. So we are done. So look at this one. So we have, we found one small technique like this, with L and so on, and use it repeatedly to get rid of the pieces in a systematic way. Actually, you have to be careful in all these things. Okay, if you are not very careful and then choose the wrong L, you will get stuck. Okay, for instance, instead of choosing this cell, if you choose this cell, and then you will know that you will get stuck after some point in time. Okay, so that, okay, after that, once you have done that one, then we used a principle of invariance. This is the only technical part of this problem, in principle of invariance. Okay, and again, most of the problems which use this concept are hard because we have to find the invariance. Here we found the invariance pretty easily, that is X, Y, Z, and so on. In fact, this invariance is very famous. The four things which we use, that is X, Y, Z, E. Okay, this is actually what is called the Klein's 4 group. And this has plenty of applications in algebra. And of course, you don't have to know this, but this group is what we used to build our invariance for this problem. This for Klein's 4 group also useful in several other problems as well, where the solitaire games were played. Okay, right. Now I hope that you enjoyed this problem. At the beginning, it looked very simple because there's a very simple rule of game playing. But as we moved along, it appeared that of course, slowly the strategies and all those things came in place. And of course, we completed the whole problem in about, meaning in quick time. But the thing is, we had two sparks of ingenuity. One is this, and then the other is that, as I said, the Klein's 4 group. So these two are the ones which hold the key for this one. Okay, right. And any comments from anyone?
Yeah, so this was definitely great. I mean, for somebody who's doing or seeing these kind of problems for the first time, they, I'm sure, would think, how does a game fall into the bucket of mathematics? And how we can use mathematical reasoning to prove something in a game. So that was quite interesting, sir. And I think the crowd online was truly glued onto the solution. But I think this kind of argument is quite new to
Yeah,
most of
mostly
them.
for
So I
most.
think,
Yeah,
yeah, so it would have been a good insight to all of them.
yeah.
And
We
yeah, I
have
think
time for one
this,
more, or we stop?
yeah, one more. I mean, we are all excited. You said you are going to solve a math problem without using mathematics. So
That
let's
was
see how
this.
that happens.
This was this
Ah, this
one.
one, right.
Yeah.
Yeah, sure.
There is one more, which
Right.
is
So
yeah.
yeah,
Be quick. I
yeah,
mean,
we
it's
can
a
we can do a
short
quick
problem.
one. Yeah.
Yeah. Yeah. So this asks that is there a sequence of 20, 25 consecutive positive integers which contain exactly 25 primes? Okay. So most of us know that controlling the number of primes in a sequence is very hard, and then it's a very highly technical problem. There is something like prime number theorem, which gives some estimates and all those things. But this appeared in a British Mathematical Olympiad. So that means that, of course, not with these numbers. Okay, so these numbers are not all that sacrosanct. It could be anything. You can say that with some limitations. You can say that is there a 10,000 consecutive positive integers we do not have, which contains exactly 100 primes? Yes, it's possible, or not possible. Okay, so that's the so this being an Olympiad problem, it should be solvable also, right? Right. The key thing is here. Can you find, first let me ask something. Can you find 10 consecutive integers with no primes? It is all of them are composite. Can we find that? Just 10 consecutive numbers, so that none is prime. None of them is prime. Or can you find 100 consecutive integers, so that there are no primes at all? Or can you find 10,000 consecutive integers, so that none of them is a prime? Or more generally, can you find n consecutive integers such that there are no primes? Now, in the first problem, we introduced a number called factorial n. What's a factorial n? It is 1 into 2 into 3 into 4 into 5, extra up to n. So if I want to find 10 consecutive integers which contain no primes at all, I will say 11 factorial plus 2, 11 factorial plus 3, so up to 11 factorial plus 10. Note that this is a multiple of 2, because 11 factorial is a multiple of 2. This is a multiple of 3. Next one is a multiple of 4. This is a multiple of 10. So none of this is a prime. None of this is a prime. So if I want n integers like this, what I have to start with? I have to start with n plus 1 factorial plus 2, n plus 1 factorial plus 3, up to n plus 1 factorial plus n plus 1. So this is a sequence of n plus 1 consecutive numbers that contain no primes. That contain no primes. So as we go along, suppose I start with 1, 2, 3. This is a number line, let us say. The number line is infinite and going to the right. So if I start with a block of, let us say, 100 numbers, as this, so I can always find 100 block somewhere along the line which do not contain any prime numbers at all. As I move along like this, okay, next block is this, next block is this, and so on. If I move along like this, there will be at least one block which I will encounter somewhere along the line which contains no primes at all. And we are done. That's all in this problem. Why is that so? Let's look at this. So I have 20, 26. So this is a sequence of 20, 25 numbers that contain no primes. Now, what about 1 to extra up to 20, 25? This one we can check. Definitely it contains more than 25 primes. It can definitely contain more than 25 primes because, see, it is 25, 50, 75, all of them. In fact, even, okay, so it contains more than 25 primes. In fact, it contains 306 primes. That we can check. We don't need that many anyway. It contains 306 primes. So what happens is that, so I have this first block, 1 to extra up to 20, 25, which starts with 306 primes. So as I move along the number line, one step at a time, that is one integer at a time. What happens number of prime numbers in this block B? Suppose I have this number and I have this number. So what will happen now? So I have the previous block is from here to here. So this block deletes this guy and includes this guy. If both of them are primes, then the number of primes will not change at all. So one prime is deleted, one prime is included. So then it will remain the same. That is, it remains the same. That is, change in the number of prime numbers will be 0. If this is not a prime and this is a prime, the number of primes increases by 1. And if this is a prime and this is not a prime, the number of primes decreases by 1. So as the block moves from the initial position 1 of 225 to this position, that is 2026 factorial plus 2, that block. So when this moves from this block to this block, the number of primes have become 0 from 306. The number of primes become 0 from 306. And every stage, it will either add, change by 1 or minus 1. It will change by 1 or minus 1. Therefore, all integer values from 0 to 306 must be taken. Correct? Okay, change only by 1 or minus 1 because it can't go from, let us say, 306 to 304. No, because it cannot change by 2 things at one step. So as I move along this number line slowly, one integer at a time, the number of primes in the block become 306 to 0. So by the nature of this change, 1 or minus 1 or 0, this becomes somewhere along the line, it has to be 25. And that's what we want. So what we have is, so we didn't exhibit a sequence of 20, 25 numbers, consecutive numbers is exactly 25 primes, but we showed that there must exist. In fact, we showed something more than that, not only 25, there is a block of numbers which contains 30 primes, 100 primes, up to 306 primes. Up to 300, actually it should contain some, meaning it should contain all, for instance, 250 primes also it should contain. So I have 306 started with, ended with 0. So all the integers in between will also be represented by this block. So for any of this, for instance, in fact, we can even generalize that to some extent. You can have n consecutive numbers with k primes where k is less than or equal to number of primes in 1 to n. So I can generalize this problem to this way. Okay. So if I just 1 to 10,000, then I can find at 10,000 sequence primes as many as this one and so on. So that's the basic idea. Here also, it required only a small strategy. And this fact, you will know as you study number theory. This is one of the first few things which you learn when you study prime numbers. So that's the only part which is used. And of course, this kind of what these are called the discrete continuity arguments. Discrete continuity. That is, if a function takes 2 values, it always changes by +1 or -1. It has to take all integer values in between. So this strategy also plays a crucial role. So to summarize, we looked at 4 different types of problems. Note that no 2 of them use the same strategy and no 2 of them had the same techniques. So we learned something about this one. So as I said in the beginning of the talk, what you need to accumulate is problem solving techniques. As you read, as you solve more and more problems, you will have your own problem solving techniques for attacking the problems which you come across in the Olympiads. So this is a very exciting journey in the IMOTP and AMOTP. There are plenty of very beautiful results which you will encounter. And again, each of them requires a bit of effort to understand and moreover to assimilate. It's not enough to just understand. Okay, you have to assimilate and then make it your own. So any technique, you have to make it your own, only then you will be able to use that, right? So in order that you will be able to use that, then definitely you need much more effort, and then keep that in your mind, and then think about that, and then meditate about that, and finally one day it will become as a second nature to you. Okay, and that's what I have in this session. And if you have any questions in the chat or others, then probably I think we can look at them.
Wow. Thank you, sir. Indeed, the last problem was a sweet dish. Uh, what I was reminded of when you said we have shown the existence that such a sequence, shown the existence of such a sequence
Yeah.
without actually finding that sequence, right? So that is amazing, right? I mean,
Yeah.
you show that something exists and without having necessarily to see that,
Yes.
which is slightly different from what happens in science as a theory. Maybe they come up with a theory that there exists something called as, let's say, black holes. A few years ago they came up with that theory,
Hmm.
but then it's still a theory until you find the existence of a black hole, right? But that is different in mathematics. You can show its existence without
Yeah.
showing where it lies.
Yeah. Yeah. In fact, not now that you asked this question, there is a technique called the probabilistic proof, which was
Mm-hmm.
perfected by uh, what is his name? I forgot the name. Okay, the probabilistic proof says that the probability of something happening is positive. That means the event has to happen sometime.
Mm-hmm.
Okay, so that kind of proofs are also there, which are very interesting to execute. Okay,
Mm-hmm.
yes, that's a very long story in any case. Yeah.
Right. So just to take a few questions that came in the chat before we close. So one was, what will happen if the child is not able to attend a particular session? Well, the recordings are available on Google Classroom, so the students can visit that. In fact, some of our students are international students, so they rely completely on the recordings. So the recordings will be available. Another question was, what if the student has doubts? Then how do we clarify them? Of course, in the class, we take in doubts, and students can stop us, how much ever they want. But periodically, we also ask if they need help sessions, and we'll be happy to organize as many help sessions as required periodically. So that is there. And many parents whose children may not have been part of online courses like this, in our observation, I think especially this generation, they have grown up with technology, so technology is just a part of them, and they don't find any difficulty in terms of gelling with online courses and things like that. So we highly recommend these programs, intermediate and advanced Math Olympiad training program, for students who are deeply passionate about mathematics. If they are class toppers and they are not challenged with good mathematics, this is where actually they can get a taste of what real mathematics is like, and who would like to push themselves and their boundaries and learn from amazing people like Muralidharan sir. He teaches combinatorics, and we have Sri Prasad Tambe sir, who teaches number theory and algebra. We have Bhas Bhamre sir, who teaches geometry. So all of them are what we can say. I mean, they are deep divers into their fields, and they are not like somebody who will be just taking any topic, even though they are experts in that. But they are deep divers in specific topics. And we will also have one of our alumni from 2014 Ram TP batch, who will also be taking some sessions this year. His name is Mihir, and you will find the faculty profile, everything on the website link, which has been pinned on the YouTube chat. And we also have Informatics Olympiad training program, which is on computer science. So we highly recommend math enthusiasts to check that as well. And we really hope that we can work with all of you And today being the last day for early bird registrations, I think it'll be good if you can take a call today in case you're planning to register. You can avail a benefit if you register by today, end of the day, right? Um, let's see if there are any other pressing questions. Okay, I think that's about it. There was one question about to say something about RAM-TP 2025. Well, we don't have a lot of information as of now, but I'll just quickly say about it maybe in a minute or two. So, Raising a Mathematician Training Program, RAM-TP, is our flagship program, which is for grade 8 to 10 students. And the idea of the program is to expose them to a wider world of mathematics than beyond school curriculum and beyond Olympiad and things like that. It's a selection-based program. About 100 students get selected across India. You can find previous years RAMTP reports on the website. So we highly recommend students to check out that and apply for that. And if you are somebody 9 to 13 years old and deeply passionate about mathematics, you are ready for high school mathematics and beyond, then Epsilon India is a great program. We encourage you to take a look at that as well. And more details are there on the website. So with that, I think we can take a pause. And for me personally, it's been an amazing session. Get an insight into what combinatorics and number theory offers, and what kind of exciting mathematics lies in store for students from grade 8 to 12. I hope all the YouTube viewers also enjoyed. Thank you all for joining us on this Sunday morning, and we look forward to interacting more with you. Um, as we close, I would request all of you to just take a look at our social media handles, and may I request Dhwani to post the social media handles or a website link on the site on the chat, so everybody who wants to follow us on WhatsApp channel or LinkedIn or Instagram, they can do that. And I think with that, we'll take a close. We'll have the video going for maybe about 30 seconds before we close. So that's about it. Thank you so much, Murli sir. And thank you everyone for the back support, Dhwani and Shreyas. Thank you so much. Yeah, I think we can stop the live streaming after Dhwani puts in the link. Right. Can we end the live streaming?